All right, good morning, good afternoon, good evening, good night, whatever it is for you to type. We're going to be taking a look at this integral here, and we're going to be looking at 4 different ways to evaluate this integral. A quick note before I get started. I've used the numbers 3 and 9 here, or negative 3, 3, and 9, just to make it convenient to get an actual numerical answer. But I could just as easily have negative absolute value of A, absolute value of A, and absolute value of A squared. I don't even need the absolute values, it could just be negative A, and A squared instead of negative 3, 3, and 9. Just be aware of that. We can use very similar rules and procedures for all integrals of such form. Alright, so the first one is one I'm going to pay least attention to because I think that's the least elegant, and that is trig substitution. Trig sub. This is the standard way to evaluate an integral of this form. I'm just going to kind of breeze over the process and not even get to the final answer because I want to focus on the other methods more. So what we would do is we would construct a triangle, a right triangle, and we would say this: if the hypotenuse is 3 and one leg is x, then the final side is 9 minus x squared. Then we're going to put some angle theta here, and then we can describe theta. Sine of theta is going to be what? It's going to be opposite over hypotenuse is x over 3. Now sine theta is x over 3, or x is equal to 3 sine of theta. We can then go back to the original expression and substitute in 3 sine theta for x. So we have the integral from minus 3 to 3 of the square root of 9 minus 3 sine squared, or 3 sine of theta squared. And again, it's a square root. We're integrating with respect to x, That is an x. And as by mistake has pointed out, that's something we're going to have to address, is you can't integrate theta with respect to x and hope to get anything useful out of this. So we need to find an expression to get for dx to find a d theta. So if we come back over here, this expression, we can take the derivative and we get dx is equal to 3 cosine theta d theta. And then we can substitute that into our integral 3 cosine theta d theta. And that gives us an integral expression that we can evaluate. From there, we can distribute, or we can square this. So the integral from negative 3 to 3 square root of 9 minus 9 sine squared theta. All of that is under the square root, and then times 3 cosine theta d theta. Here in the radical sign, we can pull out a 9. So 9 times 1 minus cosine, or sine squared, sorry, sine squared theta. And that's in a square root. I'm going to temporarily take this out of the integral just so I can show you how I'm evaluating this. Square root of 9 is 3, and 1 minus sine squared is cosine squared, so square root of cosine squared theta. When the square root of cosine squared is cosine 3 cosine of theta. So this is pretty messy and not algebraic here, but this expression eventually becomes 9 times the integral from negative 3 to 3 of cosine squared theta d theta. And this is pretty easy to evaluate. We can evaluate this and then back substitute for x. The other note is that this -3 and 3 is x equals and not theta equals. But that's the basic idea behind trig substitution. You can probably see why I am not a big fan of trig substitution. So I'm going to show you the 3 other ways to evaluate this integral, and those will all produce the same result as we would get for the above. So method number 2 is geometry. And this requires a knowledge of the function. The function is going to produce a semicircular arc in the first and second quadrants. This is a pretty bad drawing here. This is kind of what it looks like. It's a semicircle with radius 3 in the first and second quadrants, and the integral from -3 to 3 would be evaluating this area. So then we can use our geometry rules. We know that the area of a circle is equivalent to pi times the radius squared, right? In an area of a semicircle, we're going to do 1/2 times this, so 1/2 pi r squared. The radius we know is 3 squared, 1/2 pi. So this is equivalent to 9/2 pi. That way is much easier. It is less analytical, but I think that's a much more elegant solution. Now method number 3 gets a little more interesting. Method number 3, polar. This is going to also require knowledge of the function. I could show an algebraic conversion, but we're just going to use the fact that we know it's a circle, as we demonstrated, or a semicircle, as we demonstrated above. And we're going to use that knowledge to convert this to a polar function in the form of r is equal to some function of theta. Since we have a circle, and radius equals 3, in polar we are doing things in terms of the radius, r. So the polar function is simply going to be r is equal to 3, which is pretty simple. Now if we want to find the semicircle here, theta is going to be equal to 0 right here. Theta equals 0, and over this side, theta is going to be equal to pi. Okay, so now we want to evaluate some integral from 0 to pi. Now the form of a polar integral is 1/2 times the integral from alpha to beta of f of theta squared d theta. And as we've shown above, r is equal to 3, so f of theta is equal to 3 squared d theta, integral from 0 to pi, and 1/2 times all of that. So we simply evaluate this. This is 1/2 times 9 theta evaluated at pi and 0. So 1/2 times 9 times pi, so 9 pi, minus 9 times 0, which is 0. And this is equivalent to 9/2 pi, the same result we got above, and the same result we would have gotten from the first method. So that is a much more elegant analytical method you can take for the function. All right, and now method number 4, parametric. So again, we're going to use our knowledge of the function, and we can actually go straight from the polar function we had. So it is a general form that if some polar function, a polar, r is equal to f of theta, then the parametric form is x is equal to r cosine theta, y is equal to r sine theta, where theta is the parameter. So that can also be written as a t. So if our function, we have r equal to 3, then our parametric form x is equal to 3 cosine theta y is equal to 3 sine theta. And this should agree this is essentially just a unit circle that has been scaled up 3 times. So now we want to take an integral for this parametric function. It's going to be an integral from some value of y with respect to x. We have to be very careful here in this part. First, we're going to substitute. So we know y is equal to 3 sine theta. X is 3 cosine theta, which means dx is equal to negative 3 sine theta d theta. So whatever this integral is, from whatever the bounds, we're going to specify that later. Integral of 3 sine theta times negative 3 sine theta d theta. And now to consider the bounds. We want, if you remember in the diagram earlier, we want to go from this portion on the right over here to this part on the left. It's going to be similar inputs for that we used in the polar, because if you have theta is equal to 0, you will get the point 3, 3, 0. And if you have theta is equal to pi, you will get the point negative 3, 0. So we're going to put 0 and pi down as our bounds. 0 and pi. However, we're not done. You'll notice we are moving backwards, if you will. So if we are starting here, and we want to get here, we have to move in a negative direction in order to get there, right? Which means that our dx partitions are actually going to be negative. So the sign sign of dx is negative, which means we need to put a negative sign in front of our integral. An alternative way to do this would be to take the Cartesian limits of integration and use our parametric equations to convert them to new bounds of integration, and you would get the integral from negative 3 to 3 would become the integral from pi to 0. And we know that putting a negative in front of an integral is just the same thing as switching the bounds of integration. So now we can evaluate this. This is the same thing as 9 times the integral from 0 to pi of sine squared theta d theta. And sine squared theta is the same thing as 1 minus cosine of 2 theta over 2. And we're still integrating with respect to theta. So then we can pull out the 2, so we have 9/2 times the integral from 0 to pi of 1 minus cosine of 2 theta integrate with respect to theta. This is the same thing as 9/2 times theta minus 1/2 sine of 2 theta evaluated at 0 and pi. So 9/2 times pi minus 1/2 sine of 2 pi, which is 0. Start first. And then 0 minus 1/2 sine of 2 times 0, which is also 0. And so all this is equal to 9 pi over 2. And there is our answer that we have found now in 3 different ways and showed a 4th way to do it. So there you have it, the integral from negative 3 to 3 of the square root of 9 minus x squared integrated with respect to x, evaluated in 4 different ways. Thank you all so much for watching. I hope you learned something. If you have any questions or want to see a video on a particular topic, just let me know in the comments down below and I will try to get on that. Thank you so much and have a great day.